Today I'll discuss with you about simple harmonic motion. What is simple harmonic motion? So before I discuss with you about simple harmonic motion, I'd like to first introduce to you what is periodic motion. When do you call the motion to be periodic? A motion which repeats itself after a fixed time interval is called periodic motion. We call it periodic motion, right? Like for example, motion of Earth around Sun. It repeats itself after 1 year, that is 365 days and 6 hours. Repeats itself after 1 year. Like simple pendulum. Simple pendulum. A motion something like, say, I have a hemispherical bowl and I release a ball of mass m. It also is a periodic motion. It will keep on moving like this. So that's also periodic motion. So all these motions are periodic motions. They are repeating the motion. Motion repeats itself after a period of time. Now, out of this periodic motion, when do you call the motion to be oscillatory? It's a kind of periodic motion. Motion is oscillatory. When do you call the motion to be oscillatory? See, a motion is said to be oscillatory if it involves to and fro. It involves retracing of the path, right? Like this motion is, say, this is going from here and then coming back, just going like this and coming back. So it is retracing its path. It's going to this point, coming back. It's going to this point, coming back. So in one cycle, it retraces its path. It retraces its path. Even this also, it goes like this. One cycle involves retracing of the path. So we call it oscillatory motion. We call such a periodic motion oscillatory motion. Like motion of Earth around Sun is not a oscillatory motion. This is a periodic motion which is not oscillatory in nature. But motion of simple pendulum or motion of this ball in a bowl, hemispherical bowl, will be a oscillatory motion. Oscillatory motion. Now, I'll discuss with you what are the conditions which are required for the motion to be oscillatory. Let me try to discuss with you the condition for which are required for the motion to be oscillatory. The condition which must be satisfied for the motion to be oscillatory. Criteria for the motion to be oscillatory. What are the criteria for the motion to be oscillatory? See, for a motion to be oscillatory, you need to have two conditions. One, existence of point of equilibrium. Existence of the point of stable equilibrium. Second, mass. The particle which undergoes the oscillatory motion must have the mass, or the particle undergoing an oscillatory motion must have mass. So the particle undergoing an oscillatory motion must have the mass. So these are the two important criteria for the motion to be oscillatory. They are the two important criteria for the motion to be oscillatory. I'll discuss them one by one. See, first of all, I'll discuss with you what is stable equilibrium. When do you say the equilibrium to be stable? First of all, what is equilibrium? A body is said to be in equilibrium. Let me discuss the types of equilibrium. I'll discuss with you types of equilibrium. See, first of all, what is equilibrium? A body is said to be in equilibrium if the net force acting on the body is zero. On the body is zero. The net force acting on the body is zero. We say it is in equilibrium. Like you have this body of mass m. On this body, the net force is zero. N and mg both are balancing each other. So n minus mg is zero. So we call the body is in equilibrium. There are three kinds of equilibrium. One is called stable equilibrium. Other is called unstable equilibrium. And third is called neutral equilibrium. We call it neutral equilibrium, right? I'll take a good example and try to discuss with you what is stable equilibrium, what is unstable equilibrium, and when do you call the equilibrium to be neutral. See this case, you have a particle of mass m, say it is a ball, in the hemispherical bowl, BOWL, right? This is a hemispherical bowl, and I inverted this bowl and put the mass over here, and then I put it on a plane surface. There are three cases. See these three cases. This is a bowl, right? It's not ball, this is bowl. Something like this. It's an inverted bowl, right? So if I keep it here, see, in all the three cases you find that the normal reaction minus mg is zero. This normal reaction minus mg is zero. Normal reaction minus mg is zero. So in all the three cases, the particle of mass m is in equilibrium. Particle of mass m lies in equilibrium. All the surfaces I have assumed to be frictionless. So in all the three cases, the particle lies in equilibrium, right? N minus mg is zero in all the three cases. N minus mg is zero in all the three cases. All are equilibrium. But there is a difference in the nature of equilibrium. If I displace this body from its equilibrium position, it comes over here, then the particle will have tendency to come back to its equilibrium position. You can see it over here. It's mg and this is n. So if it is theta, so n minus mg cos theta will be 0 and will be balanced by mg cos theta. But there is one component mg sin theta which will try to bring this ball towards equilibrium position. So here in this case, equilibrium is such that if you displace the body from the point of equilibrium, the body tends to come back to its equilibrium position. The body tends to come back to its equilibrium position over here, right? So when you displace the body from equilibrium position, equilibrium is said to be stable. I'll call it like this. The equilibrium is said to be stable if the body was displaced from the point of equilibrium, has got a tendency to retain its equilibrium, has tendency to regain its equilibrium, has a tendency to come back to its equilibrium position. Such equilibrium is called a stable equilibrium. Whereas over here, if we displace the particle to this point, the particle do not have any tendency to regain its equilibrium position. The body will go away. It has tendency to go away from the equilibrium. Here it has a tendency to come back to its equilibrium position. So this is stable equilibrium. I'll write it over here. This is stable equilibrium. This equilibrium is said to be stable. This is unstable equilibrium. So equilibrium is said to be stable if the particle was displaced from equilibrium position has tendency to come back to equilibrium position, if there is existence of some kind of restoring tendency or some kind of restoring force or restoring torque. Whereas equilibrium is said to be unstable if particle was displaced from its equilibrium position, do not have tendency to come back to its equilibrium position but has tendency to go away from the equilibrium position. Whereas over here, if we displace the particle from its equilibrium position, the point to which you are displacing it is again equilibrium position. The point to which you displace it is again an equilibrium position. So these are the three types of equilibrium. There are three types of equilibrium. Let's discuss about what is the potential energy in this equilibrium. See, in case of stable equilibrium, at the point of equilibrium, the potential energy is minimum. You can see the potential energy of this mass. The potential energy at this point is lowest, it's minimum compared to the points in the neighborhood. If you displace the body from equilibrium position, its potential increases. So this is a point where the potential energy is minimum. This is the point where potential energy is maximum, and this is the point where potential energy is constant. If you compare the equilibrium position with the point in the neighborhood, you find that this is a point. At this point, potential energy is minimum. At this point, potential energy is maximum, and at this point, potential energy is remaining constant. So here in case of stable equilibrium, U is minimum. Here U is maximum, and here U is constant. So U is minimum as d square U by dx square is positive, or x equal here. If you describe the displacement by x variable x, you write dx square. If you are describing it by theta variable, then you write d square U by d theta square, depending on the variable which you choose in order to describe the equilibrium or the motion about equilibrium position. Here d square U by dx square will be less than 0, and here, but in all the three cases, force is 0. Force is written as minus du by dx. In all the three cases, the first derivative of the potential energy is 0, because net force acting on the body is 0. So in all the three cases, this condition holds. So this is about equilibrium position. So in case of oscillatory motion, you must have a point of stable equilibrium. Oscillatory motion always takes place about the point of stable equilibrium. Oscillatory motion always takes place about the point of stable equilibrium, right? And not just this, the body must have inertia as well. Body must have inertia as well. The stable equilibrium, the existence of stable equilibrium, one condition, the body must have inertia as well. If the body do not have inertia, the body may come back and remain at rest over here. It's only because of inertia that it overshoots. The moment it come back to equilibrium position, net force is 0. But by the time it come to this equilibrium position, if you displace the body from equilibrium to this position, the body comes back to equilibrium position. It's only because of inertia that while by the time it comes back to equilibrium position, it has already got some velocity, and due to inertia, this velocity cannot become 0 immediately. So it overshoots equilibrium position, goes to this side. Again a restoring force will act and bring the body to equilibrium position, but by the time it reaches equilibrium position, it will overshoot the equilibrium position. So here both are playing a role, one inertia, other restoring force. Or restoring force is because of the stable equilibrium. Whenever you have stable equilibrium, you will always have a restoring tendency. When you displace the particle from the equilibrium position, there will be kind of restoring force acting on the body, which will try to bring the body back to equilibrium position. So this is the kind of equilibrium which we need in case of oscillatory motion, right? Now I'll discuss with you the how to get the expression of restoring force when it displaces the particle from the equilibrium position. When you displace the particle from equilibrium position, what is the expression of restoring force? I'll discuss this.